All right, so our first speaker will be Erin Heilman. And Erin, feel free to share your screen and talk about plate boundaries and aspect. Yeah. I will give you permissions. Sorry about that. All right, try again.
Okay. So I'm going to be talking about plate boundary evolution with damage memory. This is essentially some of my PhD work that I've been working on for the past couple of years. It encompasses some of the things that I've helped implement at Aspect hackathons over the past 2 years. I also had a poster on this sort of stuff at AGU. So a little bit of background. So I'm working on global mantle convection modeling and plate tectonics with a specific rheology that we're calling a damage memory rheology. And so some of the things that have come before that were leading up to this was specifically the work by Tackley in 2000, where he looked at different types of viscosity and yield stresses and how that affects sort of the evolution of spreading centers and subduction zones in sort of a 3D box model. Specifically, the damage rheology that I'm working with comes from this 2018 paper by Fuchs and Becker, where this is showing accumulated damage or strain in a 2D box model that shows a subduction zone that has formed and is subducting. It then shuts off, and over time, there is a little sort of seed of strain that is held on in the model as it's then advected, and then over time reactivates into a new subduction zone. So I kind of took that as a jumping off point for my work, and specifically looking at how plate boundaries evolve. So both subduction zones and sort of spreading centers. And one of the hallmarks of plate tectonics on Earth at spreading centers are transform faults. And so this paper by Langemeyer et al. In 2021 did show transform faults evolving in global mantle convection models using STAG-YY, which is another mantle convection code. And they found it only through a very specific range of yield stresses was how they were able to make these transform faults come about without using really anything else in the model. So I'm looking at sort of what is the simplest model using this rheology that can show plate tectonics like it is on Earth, possibly transform faults, things like that. So the damage rheology is essentially a strain weakening and strain healing component that are put together. This is the equation for strain healing that we're using. And so it's essentially just a thermal plus time sort of strain healing. So it essentially takes the whatever already strained and damaged material, and then over a time that you prescribe, and with whatever heat that happens over time in the model, the strain is healed. And this is just kind of the accumulated damage. It's not exactly representative of it, but this is how it's implemented in the model. This is what I did at one of the hackathons. And so this is where it's implemented in the strain dependent model and how healing is used there. So for the modeling that I did, I started with 2D models because they are computationally less expensive, and I was able to run them a little faster than doing large global models. And so the framework, we started with 2 semi-temperature dependent viscosities. We had one was the Frank-Kamenetsky viscosity, which is essentially a linearized form of the Arrhenius viscosity. So this is that equation where it focuses, again, mostly on temperature, and then also use an Arrhenius viscosity to sort of see if there was going to be any differences, the overall sort of viscosity contrast, and if things would be different in the models. And so we ran basically a suite of different models, also using two types of heating. We had both bottom heated and internally heated models. Ideally, the Earth is some mixture of the two of these, but these are just sort of simpler end members that we could try and see what the differences were between those. And so we ran each with damage and without damage to also see what the differences were. So sort of the setup for the models, there's a prescribed viscosity jump at the 660 transition. We had no free surface, and there's essentially weaker yield stress in the upper mantle and then a greater yield stress in the lower mantle. And this was the setup for the rheology itself, where you have strain weakening and then strain healing. And so this is how you would set the parameters for strain healing for the models. So when we looked at these models, we saw some interesting things. So this is a bottom heated model using the Arrhenius viscosity. And looking at this model we have snapshots from different times after a model has sort of hit steady state and then continuing onward, we see that there's essentially different modes of subduction dynamics that come out of the model. And this is something that we see without changing any parameters in the model. And some of the research that I had looked at, other people see sort of these different modes of subduction dynamics, but they're changing things like plate velocity or plate strength or angle of subduction over time to get sort of these different modes. And so this is something interesting that just kind of popped out organically out of the model when we were using damage. So we have sort of this like buckling into the lower mantle, this sort of flushing or dumping type subduction, and then sort of a flat slab subduction. And so the things that I could essentially think of that might cause this are either having to do with the sort of plate thickness, because in this sort of mode 3, you can see it comes from a very thick plate. Mode 2 is sort of a thinner plate. Mode 1 is maybe in the middle, or it has to do with the velocity of the plate. So looking at the VRMS over time, I tried to sort of match up patterns of velocity to modes that we see throughout the model. And there's maybe a correlation. I don't think it's super strong. It was also difficult to see in some models that have more than one subduction zone that happen in the model space, because then it's sort of a confusing signature. Are you really seeing what's happening or not? So those were sort of interesting things we saw from 2D models, and decided then to move on to 3D to sort of look at what's happening on the surface instead of just in the mantle. So for the 3D models that we made, we're using a box geometry for now. It is sort of a large model space to keep a 6:1 aspect ratio while keeping sort of the core to mantle boundary depth. So they are large models. There's no prescribed weaknesses when we start the models. It's only a prescribed temperature at the top, and then the mantle temperature is also prescribed. So these models were run on Frontera using about 8 nodes and 448 cores for generally 1 to 2 weeks that they would have to run for. They are very large models with very large viscosity contrasts, so they end up taking some time. So this is a map view looking down on the 2 different models. So the only differences between these is if it's using the damage rheology or not. So on the left, there's no damage used, and on the right, there is damage. And so this is looking at the viscosity field, and sort of the number one takeaway that we could see is when you use the damage rheology, you see a lot more strain localization in some of these spreading centers. And so for reference, the orange is going to be where the subduction zones are, and then the lighter blue and the viscosity is going to be the spreading ridges. And so without damage, you can see sort of more of the surface is kind of broken up and fractured with the spreading ridges. They're not very localized. Subduction zones look relatively the same. Yeah, and so that is what it looks like in the viscosity. And there is sort of interesting, almost braided fault overlapping structures, which seems to be just kind of the preferred mode of how the spreading centers sort of move over time in these models. But looking at the total accumulated strain in these models, you can really see where the damage rheology comes into play. So this is without a damage rheology, and you get a high, very deformed model without it, where you can still see sort of where the subduction zones are splitting the strain. And then looking at the model with a damage rheology and that strain healing in it, the values of the total strain are much lower, and you can see that much more of the surface is sort of unstrained. And this is what we wanted, and sort of what you would maybe expect to see over time, is that, you know, not every single plate is deforming everywhere all the time. So looking at these two sort of in motion, on the left, you can see sort of where these very broad patches of sort of spreading centers then merge and go into sort of a dumping in a subduction zone. So this is what the strain looks like in the mantle. And so then on the right, this is where we have the damage. So this long line, for example, is a spreading center. So you can see it kind of move away, and there is your subduction zone there as well. And so in the total strain on the bottom right here, where we have our damage rheology, you can see where there is strain at the subduction zone. And here, when it comes around again, there will be sort of a dumping of a slab that eventually goes away. And this is sort of what we expect to see. You don't expect there to be tons of strain held in the mantle just because it is hot. And we don't think that that's essentially what's happening. So we're happy to see this. And we do also see, not exactly here, but periods of subduction reinitiation, like from one of the earlier papers that uses the damage rheology as well. So this is the same model with damage at a different time, showing a couple different things. So we have viscosity, the total accumulated strain, the cohesions, which is essentially the yield stress in the model, and then temperature in a cross section showing the movement of these subduction zones here. And so you can kind of see the interesting curvature of the spreading centers that sort of diffuse out and then get sucked into the subduction zone. And you can kind of see that happening in the yield stress as well, where it's deforming. You can also kind of watch the subduction zones and how they interact with the 660 transition, where you have the viscosity jump as well. So in movement, it's very interesting. But partially what we're trying to look at is the plate boundary evolution. And so this is a close-up of a time period. These are sort of the same, they're the same area looking at two different time steps. And so we have viscosity, the total accumulated strain, and then the velocity field for these areas. So at this first time step, you can see these two parallel spreading ridges that are looking like they're about to intersect with another. And this here is going to be your subduction zone. So looking at it in the velocity, you can kind of see the cutoff there, there, and there of the different spreading ridges. The overall pattern is that it's moving down towards the subduction zone. And at the next time step, you can see kind of how the two parallel spreading ridges have sort of sucked into the spreading ridge above. So we aren't exactly seeing, you know, strong step over transform faults in these models yet. But we are seeing sort of interesting dynamics. And again, you can kind of see almost a 90-degree angle maybe there in the strain, and again in the velocity. So we're not exactly there with transform faults yet. which is okay so far, because we've seen that the damage rheology is successful in helping with the strain localization that we want to see in the surface. Some things moving forward would be to increase the resolution in spreading centers so that we can hopefully see a stronger delineation of what's happening there, as well as moving on to using a 3D spherical geometry to try and see if that sphericity does have an overall effect on transform fault formation, like we think it might. So thank you.
Awesome. Thank you very much. Those are some very pretty models. Also very interesting, and we'll get to questions later. That would bring us to our second talk of the session. The second talk will be given by Daniel Douglas about magma-assisted flexure in Hawaiian lithosphere. And Daniel, I also need to give you permissions. You should have permissions now.
Let me see. Sorry, just one sec. I got a new laptop and I need to give it permission for Zoom. Do you see that okay?
Yeah, not yet as full screen, but there we go. That looks good. Yes.
Okay. Cool. Yeah. Hey everyone. My name is Daniel. I'm currently a PhD student with John Nalaboff at New Mexico Tech. I just started a few months ago, but I'm going to be presenting a kind of summary of the master's thesis that I did in Hawaii with Garrett Ito. And yeah, the thesis is titled Magma-Assisted Lithospheric Flexure beneath Hawaii, inferred from geodynamic models, which of course are aspect models, and active source seismology. So I'm going to start by just explaining what lithospheric flexure is, in case some of you haven't really taken a dive into that topic too closely. Then I'm going to summarize a previous study that someone else did when they modeled lithospheric flexure under the Hawaiian Islands. And when I summarize that work, it'll sort of bring to light this dilemma that we tried to answer with my work, which is that Hawaiian lithosphere appears weak in reality compared to when you model it. And that brings about the question of whether laboratory-derived rheologies need to be revised in order to fit Hawaiian lithosphere behavior, or if the lithosphere beneath Hawaii is weakened some other way, such as thermally from magmatic heating. And so, yeah, I'll start just by outlining what lithospheric flexure is. It's the response of the lithosphere due to a topographic load. And this response can be elastic or viscous, depending on the time scales. And I'm showing a little cartoon here on the right, which is showing sort of the characteristic profile of what flexure looks like. We have these two yellow plates. The difference between the top and the bottom is that the top is stronger than the bottom. And we have this pink island load that's being placed downward onto the lithosphere. And relative to these black dashed lines, which is the undeformed lithosphere, you can see that you get downward flexure beneath the island, and then uplift sort of distally away from the island. And this is sort of the characteristic shape of what flexure looks like in the lithosphere. And you can observe this through seismic imaging and through gravity anomaly studies. And you see this sort of flexure at subduction zones and underneath seamounts and island chains like the Hawaiian Islands. And you can actually infer something about lithospheric properties from what the flexural profile looks like, because as you can see between these two different scenarios, a weaker plate has more flexure and sort of a smaller flexural wavelength, which is the distance between this high amplitude uplift and the high amplitude depression. And so this is where lithospheric modeling comes in, because if you have the observations of flexure, if you can reproduce those observations in models, you can kind of say that this is the rheology that gave me the observations. So this could be what the lithosphere rheology actually is in reality, since my models reproduced it. But in order to do this kind of modeling, you need a good way to set up the lithosphere of the rheology in your calculations. And so for the models I'm going to show you later, we use the viscoelastic plastic rheology, which has all of this sort of intricate complications of temperature dependence and stress dependence and pressure dependence, etc. But the regimes of lithosphere rheology can sort of be divided into three dominating areas, which is brittle deformation in the shallowest parts of the lithosphere. Then you have low temperature ductile creep at mid depths, and then high temperature ductile creep at larger depths. And thankfully, all three of these regimes are sort of natively incorporated into aspects. So setting up like a viscoelastic plastic rheology in theory isn't too hard. It's just making sure it's stable as your models, but the functionality is all sort of there. But for this work, I'm going to be sort of focusing on the low temperature ductile creep regime. And so that brings me to the previous study that I want to highlight. I'm going to talk about the study by Bellis et al. From 2020. And I'm showing a couple figures from their study here. The center image is a map of the Hawaiian Islands, the imagery map. And these three white lines that you see around the island of Oahu are the locations of seismic transects, where shipboard imagery of the top of the oceanic crust was collected. Excuse me. And you can see what that looks like on these panels to the left and right. I'll start on the left side here. These are amount of flexure on the y-axis versus distance along the seismic profile on the x-axis. And the black dots represent the observed physical flexure of the lithosphere along each of these profiles. And then the red dots in both of these side panels represents the calculated flexure in this study's models of flexure. And the difference between the left and the right is that the left profiles are using laboratory-defined low-temperature ductile creep rheologies. So as defined by experiments plugged into their modeling code, which was an aspect, I don't remember what code they used, but using laboratory flow laws, they see that clearly you're under-predicting the observations. These red dots do not reproduce observations at all. And they found that in order to get these fits on the right, which clearly are an improvement to the data set, you had to take this activation energy, EP, in this rheological equation and alter it, decrease it by up to 40% in order to fit the data set. And so this is sort of the motivation for my master's work, which is there a way to sort of get around this apparent weakness of the Hawaiian lithosphere without needing to change laboratory-defined parameters? And part of the motivation for this came from the study by Guest et al. In 2020, which looked at xenolith samples erupted from beneath the island of Oahu. And I'm showing a figure from that study here. This is a depth versus temperature plot. And we're seeing cross-cutting this plot different geotherms from the Parsons and Slater plate model of varying seafloor age. So we have at the bottom here, this bold black line is the 90 million year geotherm, and then sort of decreasing up to a 20 million year geotherm up here. And the important thing to take away from this plot is that sort of average accepted age of Hawaiian lithosphere is 90 million year old seafloor. But these colored squares and blue circles represent the xenolith samples that I mentioned came from beneath the island of Oahu. And clearly these formed at pressures and temperatures that are not representative of this 90 million year geotherm is significantly hotter than predicted by this. And if we look at that rheological equation again, if we increase temperature, we'll weaken the lithosphere and it'll be more easy to deform, which should be intuitive anyway. And so with all that background, I'll get into what my models look like and sort of the main features of it. I'm showing a picture here on the right at the last time step of one of my models, and we're looking at the vertical stress field. You can see at the top boundary here, the free surface, we have a clear outline of what the islands look like. So you can see the stresses are reflecting where the islands are located, which is good. And then we have open boundaries on the sides here, all four sides, and then no slip boundary on the bottom for stability. The way that we initialized the temperature structure in my models was using the seafloor age map from Muller, 2016, I believe. And we implemented that by using the Parsons and Slater plate cooling model to define the temperature with depth everywhere. We grew the islands of Hawaii over 6 million years. So every single time steps for 5,000 years. The traction due to the growth of the islands was updated. And then we also implemented into Aspect, this is something I did at one of the hackathons, a way to calculate a dynamic part of the load, which simulates the infilling of material into the flexural mode. So you can imagine that, as the island builds and the lithosphere is compressed, that moat part is going to be infilled with material like sediment or volcanic edifice in the case of an island shape like this. And if you're not accounting for that additional load, you're severely under predicting the magnitude of the load in your models. So yeah, we grew the islands over 6 million years, and how we did that was using 17 different main shield volcanoes at various points along the chain, and I'm showing a map of where those are located here, and an animation of what that growth looks like through time on the bottom right. And yeah, we essentially converted those into track sheets, implemented them into ASCII files, and then applied those to the top of the free surface to model the way that the islands load the lithosphere. And then the last part of the models is the heating model, which is important since that's sort of what I'm testing. We use the method for heating called thermal rejuvenation, and we localize this heating to beneath the footprint of the islands, since that's where our xenolith samples came from, beneath the islands. And everywhere within this black contour that you can see in this map here is subject to some degree of heating by thermal rejuvenation. And thermal rejuvenation, if you're not familiar, I'm showing an example of what that looks like in this bottom right animation. It essentially takes a geotherm of a given age, in this case a 90 million year geotherm, and it reduces the age to a different effective age, thereby heating the entire plate throughout. And so here we're going from a 90 million year to a 40 million year old geotherm, which corresponds to a 50 million year equivalent thermal rejuvenation. And we coupled this heating model directly to the loading model in order to sort of simulate to first order how the magma, which is like ascending through the lithosphere, erupting at the surface and building the load, would advectively and diffusely heat the lithosphere as it ascends through the lithosphere. And then lastly, before I show some results, the observations that we use to constrain our models, we use two different sets of active source seismic data that was collected shipboard. The first was the data set which I showed you that previous study had, centered around the island of Oahu. These are these green lines here. And this was collected in 1989 for the RV Conrad. And then we have this new data set collected in 2018, which are these cyan lines, which run parallel and perpendicular to the island chain. There's also other data sets like tomographic conversions and flexure rates from drowned corals, but just in the interest of time, I'm not going to really talk about those. I'm only going to talk about these 6 profiles here, and I'm only going to talk about one of the rheologies that we tested. We did test 3, but again, in the interest of time, I'm just going to focus on this rheology, which is the Cranch 2016 low temperature creep rheology. And I'm only going to talk about 3 of these colors on this legend here. The most important one is this gray color, which is the seismic data. So the actual observations of flexure along various transects along the island chain. And then I'm going to focus on this black dash line, which is the previous study's preferred method of weakening rheology to fit the data set. So whenever we see these black dash line, that's the other study's method. And then I'm going to focus on this orange line, which is my best sort of fitting method, which is a thermal rejuvenation of 50 million years. And so starting on the left side, all 6 of these plots are just amount of flexure on the y-axis versus distance along the corresponding profile on the x. But we can see that for all 3 of these profiles, which are centralized around the island of Oahu, we get similar fit quality between my method and the other study's method. The black dash line and the orange lines are providing similar qualities of fit to the data set along these 3 lines, which is good because that proves that we're in agreement with the previous study around this part of the island chain, which is older and most likely reached equilibrium in flexure since it's 4 million or so years old. But the sort of fits become more interesting as we go towards the younger side of the chain, and most notably this plot down here, which is this line that cuts between Maui and Big Island, a much younger part of the island chain. We see that their models severely overpredict the flexure here by several kilometers, whereas our models do also provide some overprediction of the flexure, but it's more on the order of a couple hundred meters as opposed to a couple kilometers, so an order of magnitude difference there. And this fit quality of our model sort of persists along all parts of the island chain, not just at the Oahu side of the chain. And so, yeah, that brings me to the end. Not shown here were the other 3 rheologies that we tested. I showed you the Cranch et al. 2016 low temperature flow law. which saw an improvement to the fit. We also tested the Adrisi 2016 low temperature rheology and the May 2010 rheology. And we found that, at least for the Cranston Adrisi, this method of thermal weakening was able to provide significant improvements to fit along all parts of the chain without needing to alter the laboratory defined parameters. However, the May rheology still proved to be too strong to overcome this weakness using our thermal model. So that is it. And I guess questions will be for later, so ignore that.
Awesome. Thank you, Daniel.
Don't know how to stop. Oh, stop sharing. There we go.
All right. That brings us to the last talk of this first presentation session. And that will be given by Fiona Clerc about deglaciation-enhanced Mantle CO2 fluxes at Yellowstone. And Fiona, I will give you permissions. Try to share your screen now. That should work.
Okay.
Excellent. We can see your screen.
Okay. Is this the
and we can hear you. Excellent.
Okay, perfect. Great. And this
Go
is
ahead.
the interview, right? Or the full view.
This is the correct view, the one that we need to see.
Great. Okay, so hi everyone. Welcome to my talk. My name is Fiona. I'm a PhD student working with Mark Behn and Brent Minchew. And so using Aspect, we modeled how the retreat of a Yellowstone ice cap could have enhanced melt generation and extracted additional CO2 from the mantle, which if released to the surface could imply a positive feedback between deglaciation and climate warming. And if you're interested, please check out the preprint on Earth Archive or contact me by email. So the retreat of ice sheets can influence magmatic systems, illustrated from left to right. As an ice sheet retreats, the mantle rebounds, which can reduce pressures in the mantle and enhance melting in areas which are already partially molten, illustrated by the yellow field. Enhanced melting can in turn increase magmatic or volcanic activity to the surface, which can potentially trigger outburst flooding from glacial lakes, or it can accelerate the flow of glaciers by heating their base. So that's these red arrows. And then increased explosive volcanism can release aerosols into the atmosphere, which can influence the Earth's climate. And finally, enhanced mantle melting can extract additional CO2 from the mantle, which if released to the surface can also contribute to these positive feedbacks between climate warming and deglaciation. So now the magmatic CO2 feedback may have been important during the last deglaciation. So scalings of eruptive records estimate that the additional CO2 from subaerial volcanoes is on the order of 1,000 gigatons. So on the right, it's a plot from Hoybers and Langmuir in which they estimate that the additional extra eruptions on the top plot could have raised atmospheric levels by as much as 40 ppm, which is the difference between the two lines on the bottom plot. However, these estimates come from eruptive records and they're potentially missing contributions from areas which are currently inaccessible, such as under ice. And they could also be missing contributions from like diffuse emissions like hydrothermal systems or dormant volcanoes, which make up roughly half of the modern global volcanic flux. And in particular, Yellowstone hasn't erupted for 70,000 years, but still currently contributes a globally significant mass of CO2. And so this raises the question of, was the mantle CO2 flux from Yellowstone magnified due to enhanced melting during recent deglaciations? So answering this question is tricky as the link between deglaciation and enhanced mantle melting is most strongly established in Iceland, which is tectonically different from Yellowstone due to the presence of the mantle plume and the spreading ridge. So in Iceland, there was an increase in eruptive volume. So the slope of the line is greatest during this deglaciation interval around 11,000 years ago. And so this effect of enhanced mantle melting in response to deglaciation was first modeled by Gell and Mackenzie in the top right. And their models are able to explain both the enhanced eruption rates and these depletions in trace element geochemistry. So that's the difference between the orange line and the gray lines. So again, in other settings, it's less clear how this process operates, as there are a few forward models that consider how mantle melting may be affected. And in particular, it's unclear how continental settings would respond due to their thicker lithosphere. So this brings us to Yellowstone as a useful comparison. For instance, so some tectonic similarities are that it is magmatically active and potentially has a mantle plume. The ice cap is slightly smaller, but also rapidly deglaciated rapidly over several thousands of years. So however, the difference with Iceland is that there's no evidence that volcanism was enhanced during deglaciation. So on the bottom, I'm showing the most recent spate of eruptive episode. And there are really no anomalous trends at any, I would say at any point during this interval, in particular during this deglaciation around 140,000 years ago. Oh, and then the right is just a reconstruction of the Yellowstone glacial system for the last deglaciation and the penultimate one as well. So as we know that these high mantle CO2 fluxes in Yellowstone are released in the absence of eruptions, we can model the influence of deglaciation on both magmatism and CO2 release. Okay. So then these figures show how the models are set up in aspect. So we're going to do both systems, both Iceland as a benchmark and Yellowstone on the right. And we'll study changes in pressure and in melt generation due to glacial unloading. So the models are set up in 2 dimensions. The rheology is viscoelastic and temperature dependent. So we get this cold rigid lithosphere in blue overlying a warm viscous asthenosphere. We place a plume on or a thermal anomaly on the bottom boundary to generate a plume as the model is spun up to steady state. And the model is driven by the spreading the plate motions applied on the surface. And yeah, and so then once the model is spun up to steady state, then we load and unload this free surface using pressure boundary conditions on the top. And those are represented by the green parabolas. And they're vertically exaggerated in this figure. And then the bottom plot shows the melt fractions. So these are, I guess these are like the degree of melting. So they're solely dependent on pressure and temperature for a dry peridotite solidus. Okay, so now I'll show the model results. This is a background time step. So this is prior. So this is in steady state prior to any loading or unloading. On the left, I'm showing the rate of pressure change. So in teal, it's negative and the mantle is decompressing, which would encourage melting. And the red arrows show the flow of the lithosphere. So it's driven by plate shearing, but there's also this component of uplift from the plume. And on the right is the rate of melt generation. So it's positive in orange. So that's where the mantle is melting. And melts are being produced at depths of 70 to 90 kilometers, which are consistent with geophysical and geochemical estimates. And if we were to integrate these positive rates volumetrically, we get a background rate of 0.02 kilometers cubed, which is consistent with estimates from the emplacement of eruptive result volumes. And then we'll later also test higher rates consistent with alternative estimates. Okay, and then on the bottom, I'm now showing a time step during which the model is being unloaded. So again, the green field shows the present ice extent at that time step. And the mantle rebounds, which leads to greater rates of decompression in deeper teal, and greater rates of melt generation over a wider extent. And comparing these two melt generation rates, we find that melting is enhanced 19-fold during deglaciation relative to the background, which over the entire deglaciation interval represents 815 kilometers cubed of extra melt. If we compare the trace element depletion, it's likely too small to be resolvable in at least in available data sets. The presence of a plume beneath Yellowstone is controversial, so we also test models in which we don't have a plume tail and just have like a thermal anomaly, and those and that has a limited influence on the result. And we also test higher background melting rates, and those generally generate greater deglacial melt volumes. So those melt volumes generally scale with the background rate. Okay, so now I'll just take the volumetrically integrated rate of melt generation to show how it evolves through time. So on the top left is just the ice volume used in the model forcing as the top boundary condition. So the red line is the ice volume for Yellowstone, and it decreases linearly through the deglaciation interval of 2,000 years, indicated by the pink shading. In the middle is the rate of melt generation. So in black, we're seeing this enhanced melting relative to the background in orange. And then on the bottom, I'm showing the rate at which CO2 is being extracted by the melts within the mantle. And so we use a range of mantle CO2 concentrations of 120 to 400 ppm in order to match these interpolated observed modern fluxes indicated by the purple bar. And so we see that during the deglaciation, the CO2 flux is enhanced relative to the background, and that the extra CO2 extracted throughout the deglaciation is 50 to 180 gigatons. To give you a sense of scale, so this extra CO2, if released today, would increase the modern global volcanic flux by 9 to 31%, and would be significant relative to the extra 1,000 gigatons of global volcanic CO2 that may have been released during the last deglaciation. Okay, so this extra CO2 can presumably seep up to the surface, but the fate of the additional melts is unclear, given that the Yellowstone magmatic system is rather complex. That's illustrated on the right. Potentially the melt could be fed into this deeper basaltic reservoir and eventually make its way up to this rhyolitic chamber. But again, the absence of a recorded eruptive response would indicate that all these crustal processes are really hindering the surface expression of this enhanced mantle melting. And regarding our CO2 flux, right, our model is really only estimating the mass of CO2 that could be released, and doesn't really place any constraint at the rate at which it could be reaching the surface. Okay. So finally, going back to the plots of the model evolution through time, I've just added the results from Iceland on the right. And so the point of doing Iceland was to have it as a benchmark. So for Iceland, we do match both the background and enhanced fluxes for the melting rate and the CO2 fluxes against existing studies. And then if we compare the relative enhancement of like melt production and CO2 fluxes for both systems, we find that this enhancement is comparable in both settings. So it may be unintuitive that this effect would also be important beneath thicker lithosphere. But we did do some comparisons of our results to analytical solutions, and to first order, the pressure changes are going to be important at depths that are equivalent to the width of the ice sheet, which implies that other continental hotspots that are overlain by extensive ice masses could undergo enhanced mantle melting during deglaciation. So in particular, West Antarctica bears some tectonic similarities to Yellowstone, so it could also be interesting. So it's volcanically active. It's deglaciated rapidly in the past. The lithosphere is only 60 to 110 kilometers thick. There may be mantle plumes. Some regions are rich in CO2. And then there's evidence that some volcanic features shown on the right by the letters that these are associated with areas of enhanced basal melting and ice flow. So it would be plausible that the large rates of mantle decompression under the collapse of a West Antarctic ice sheet could generate melting and release CO2 or heat the base of the ice sheets and initiate these positive feedbacks. Okay. In conclusion, we found that the deglaciation of the Yellowstone ice cap did enhance melting in the mantle and would have released or extracted large amounts of CO2, enough to play a role in these climate feedbacks, and that this effect could also be important in other systems, for example, West Antarctica. Thank you.
Excellent. Thank you so much. I think all of our speakers deserve a round of applause for their presentations. And that will bring us to the first discussion session.